Hey everyone, and welcome. Today we are diving into a classic coding problem that you see everywhere, from trending topics on social media to bestseller lists online. It's the top K frequent words problem, and you're going to want to stick around for this one, because by the end, you'll have this powerful pattern that'll help you solve a whole class of similar problems.
Have you ever stopped to wonder how a service like YouTube figures out what's trending? I mean, think about it. They can't be sorting through billions of videos every single second. There has to be a much smarter, way more efficient way to find the top items in these enormous datasets. And that, right there, is the core of the puzzle we're tackling today.
Okay, so first things first. What exactly are we trying to do here? Let's lay out the rules of the game. All right, so there are really two key things we have to get right. First, pretty obvious, we need to find the words that pop up the most often. Second, we need to sort those top words by their frequency, going from the highest all the way down to the lowest. And here's the tricky part, the tiebreaker. If two words show up the exact same number of times, the one that comes first alphabetically wins.
You know, no matter which fancy algorithm we end up using, our first step is always going to be the same. We have to count how many times each unique word appears. A hash map is perfect for this. So for our list here, we just go through and tally it up. Go shows up 3 times, byte 2 times, and so on. Easy enough, right?
So now that we've got our counts, how do we actually find the top K items? Well, a really intuitive way to start thinking about this is with a data structure that's literally built for finding the biggest thing, a max heap. So what is a max heap? Well, it's this awesome tree-like structure that has one simple, super powerful rule. It always keeps the largest element right at the very top. So we can just take all of our word frequency pairs and dump them into the heap. It'll automatically shuffle everything around to make sure the item with the highest frequency, in our case, Go 3, is just sitting there at the top, ready for us to grab. And once we've done that, the rest is honestly a piece of cake. If we want the top 2 items, we just pluck the top element off the heap. So we grab Go 3, the heap instantly reorganizes itself, and now byte 2 is the new king of the hill. We grab that one too, and that's it. We have our answer. It's clean, it's direct, it works. Okay, so let's talk about the price we pay for this approach. Time-wise, it takes about O of n to build the heap with all of our items. Then, for each of the k items we want, we have to do a pop operation which costs O of log n. But the real issue here, the one to keep an eye on, is space. We have to store all n unique words in our heap. And that's a huge deal if n is, a million words and k is only 10.
And this is the question you're almost guaranteed to get in an interview. The max heap solution works, for sure. But is it the best we can do? It just feels a little wasteful to store everything when we only care about a tiny fraction of the data. So, can we do better? Can we nail that space complexity?
All right, now let's get to the great solution, the really clever one. And it's going to sound a little weird at first, but trust me on this. We're going to use a min heap to find the max items. This is the big aha moment right here. I want you to think of our heap like a VIP lounge, and it only has room for K people. Now, instead of trying to find the most important person in the entire building, we're just going to keep track of the K most important people we've seen so far. Our min heap is going to be the bouncer at the door, and if a new person shows up who's more important than the least important person currently inside the lounge, well, we kick the least important one out and let the new VIP in. Okay, let's walk through this step by step. Our VIP lounge has a capacity of 2, so K equals 2. Let's say we've already seen a few words, and right now, Go 3 and coding 1 are inside. Now, byte 2 comes along, we let it in for a moment to check its credentials, and whoops, now we have 3 items, and that's one too many. So since we're over capacity, the bouncer has to do their job. And because we're using a min heap, finding the least important person, the one with the lowest frequency, is super easy. It's always right there at the top. So we just pop coding 1 and kick it out of the lounge. The heap is back to size 2, and now it contains an even stronger set of top candidates. And we just keep doing this over and over again for every single word in our list. By the time we've checked them all, our heap, our VIP lounge, is guaranteed to be holding the actual K most frequent words from the entire dataset. It's like this constant rolling process of kicking out the weakest link to make sure only the strongest survive. Okay, so the heap has our top K items. We're almost there, we just have to pull them out and present them correctly. Now remember, this is a min heap, so when we start popping things out, they're going to come out from lowest frequency to highest. So we pop them all out, which gives us a list from smallest to biggest, and then boom, we just reverse it, and there's our final, perfectly sorted result.
And would you just look at the difference this makes in complexity? The time is now O of n log k. Why log k and not log n? Because every push and pop operation is on a heap that never gets bigger than size k. That is a massive win. And even better is the space. It's just OK. We're not storing the entire dictionary anymore, just the top contenders.
So let's do a little showdown, a head-to-head comparison, just to see exactly why this min heap trick is so much better for this specific problem.
Yeah, this table really says it all, doesn't it? Think about it. When you're trying to find the top 10 trending topics out of millions of tweets, k is way, way smaller than n. The min heap's time complexity is a great improvement for sure, but the space complexity, O of k versus O of n, that's not just an improvement, that's a total game changer. But the real prize here isn't just solving this one problem. It's about training your brain to see the pattern. So the next time you see a problem that even smells like this one, you know exactly what to do. This right here, this is the money quote. Anytime a problem asks you to find the top k of anything, the k smallest distances, the k largest values, the k most frequent items, your mind should just snap right to it. Heap. This is a job for a heap.
Seriously, it's that simple. This pattern is one of the most useful ones you can possibly add to your toolkit. If you see top K, you think heap. It will point you straight to an efficient solution almost every time.
Okay, I'm going to leave you with a little food for thought. We've established that the min heap is way better when k is small compared to n. But what if k is huge? What if you need to find the top 99,000 items out of 100,000? All of a sudden, those complexities start to look a lot more similar, don't they? And maybe that simpler, more direct max heap approach isn't so bad after all. Thinking about these kinds of edge cases and trade-offs, that's what really takes you to the next level as a developer.